Hey everyone, welcome back. We're going to continue with the alternating series test. Before we get to the sum estimations, I just wanted to review again the absolute convergence and state the absolute convergence theorem. So let me see. The absolute convergence theorem tells us that if the absolute value of a given alternating series converges, then the series converges, the original series without the absolute value converges absolutely. So sometimes when trying to determine if a alternating series converges, you can just take the absolute value of it, see if that converges, because then the whole series will converge. So the series converges absolutely. If the series, the absolute value of a alternating series diverges, then the original series, in the original series converge, then the series converges conditionally. Let me erase this and say, and A sub n converges. Right, so if the absolute value diverges but the regular alternating series converges, then we say that the alternating series converges conditionally. So we saw examples of that with the ln 1 over n 1 over n ln of n alternating. We saw that by the alternating series, right? It was decreasing, the limit was to 0, so it converges by alternating series test. But the absolute value did not converge, so the absolute value diverges, and so we say this converges conditionally. Whereas this one up here, when we look at the series as alternating, it converges. When we look at the series with the absolute value, right, to check for absolute convergence, this is just a series 1 over 3 to the n, right? The absolute value gets rid of the negative essentially, and this is a geometric series with r equals to 1/3, which is less than 1, so it converges. So here the absolute value converges, so then the series, the original series, we can say converges absolutely. So those are good examples of the absolute convergence theorem. So oftentimes with an alternating series, especially if it looks geometric or like a P with the condition of P that it might converge, I may just look at the absolute value, because if the absolute value converges, then the whole series converges. All right, now let's go look at the estimating sums. So we can estimate a sum by, if it's an alternating series. We can also do it for the integral test. I didn't mention that when we did the integral test, so I'll mention at the end of this. So if the alternating series test applies and we get a series that will converge, then the remainder of the sum that becomes the error of the sum and approximation is the absolute value of Rn is less than a sub n plus 1, so less than the next term. So what this says essentially, if you have a series that converges, so let's say if we show that the series converges, right? To converge means it has a sum, then S is equal to that sum. And so when we have an approximation, Rn, so the whole sum is essentially the approximation. So for, let me call it Sn. So if I go n terms, here n is 6, so I was going to use that example, but let's do it in general. So it will be the however many terms I want to say I want to approximate using the first 10 terms, the first 100 terms. So this is an infinite sum, big S. Sn is not, right? It's a sum of the first 100 terms, the first 6 terms. And so what that means really is that I'm going to have, right, A1 plus A2 plus A3 plus A4 plus, I'm kind of ignoring the alternating part, but plus A7, and then you're going to have plus A7 plus 1 plus A7 plus 2 plus dot 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 forever and ever and ever. And so what we're saying is that, well, I'm going to approximate the sum of the first n terms, so that's Sn, which means that what remains is appropriately called the remainder of n terms. So that's where this is coming from. So the total sum is then Sn plus Rn, or sum estimation, plus the remainder, which then if I solve for the remainder, we get that, right, subtract Sn from both sides, so Rn is equal to the whole sum minus Sn. So that's kind of what this is saying. But it's really that the sum is our Sn plus our Rn. So this is what we really want to remember. So in this case, I'm trying to estimate a sum for the first 6 terms of this. So back to this example. Does it converge? Yes, it actually converges absolutely. This is the example from above. So we're going to start. So our S then is going to be the first term. So when n is 0, so that's just 1 all around. And then minus, right now we start alternating when n is 1. So minus 1/3 plus 1/9 minus 1 over 27 plus 1 over 81. How many terms is that? 1, 2, 3, 4, 5. We need one more. Minus 1 over 243. And then plus dot, 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 right? That becomes our Rn. So this is our Sn, right? So this is S6, the sum of the first 6 terms. So in this sum, notice that we started with n equals 0. Now, remember, for sequences, you have to start at n equals 1, but for series, you can really start anywhere. So this starts at n equals 0. So 0, 1, 2, 3, 4, 5, oh, n equals 6. So we're going to go plus the next term. So 1 over what's 3 to the 6 is 729. So this will be our S. It's not really S6 then, it's S7. So this is a little weird because it asks for when n is 6. So because we start at 0, n is 6 actually gives us 7 terms. Right, because that's n equals 0, n equals 1, 2, 3, 4, 5, 6. Had I said find S6, right, S6 will be the sum of the first 6 terms. But this says approximate the sum for when n equals 6. So n equals 6, because we started at 0, it gives us actually 7 terms. And so over here, we're going to have plus, and then the next one. And because it's alternating, it's actually minus. So minus 1 over, so 3 to the 0, 1, 2, 3, 4, 5, 6. So 3 to the 7th, 2,187. And then plus dot, dot, dot. And so this becomes our R7, right, for n equals 6. So then this is our sum. Now notice in this theorem, it says the error in the sum approximation is Rn less than A7 plus 1. So that's why I went to the next one, right? This is my when n equals 6, and so my n plus 1 is this one. So n plus 1 is 7. So this tells me that I added another page here. So I know that the error in the approximation is R7 is less than 1 over 2187, because we're doing the absolute value. So that means that my sum approximation will be then 1 minus 1/3 plus 1/9 minus 1 over 27 plus 1 over 81 minus 1 over 243 plus 1 over 729, and then my error, meaning that the whole other thing, the whole rest of this is going to be smaller than the next term. And this makes sense because we already said that this converges, right? So if this converges, the limit is going to 0, and so all of these terms are getting smaller, so it's decreasing, it's going to 0, so all of this is going to be in your alternating, so this is going to be the largest term, so you're going to be, the remainder is going to be smaller than that. And so we can say then the sum approximation is the sum of the first 7 terms plus the remainder, and the remainder is smaller than this, so plus 1 over 2187, right? And so this is because our remainder is smaller than that, and so this will give us the sum approximation. So once I add all these up and then add the remainder, 1 over 2187, I'll get an approximation for the sum. And so when I put all that on my calculator, I get 0.750800. Let's go to 6 decimal places. So 1, 2, 3, 4, 5, 6. It's a 1 after that. So this will be my approximation for the sum. Now notice that this was an alternating geometric, right? That's what it was. So we can, starting at 0, so we can combine, right? These are the same exponents, so I can say this is really n equals 0 to the infinity of negative 1/3 to the n. This is still geometric, with r equals to 1/3, negative 1/3, and remember this converges if the absolute value of r is less than 1. So the absolute value of negative 1/3 is positive 1/3, which is less than 1, so it converges. And the geometric series allows us to find the sum, right? The sum is the first term over 1 minus the ratio. So in our case, the first term is when n is 0, so you get just 1, and we can see it up here. The first term is 1 over 1 minus 1/3. So it's 1 over 2/3, which is, right, 1 minus 1/3 is 2/3. So this is, wait, hang on. The ratio is negative 1/3. Let me go back over here. So this is minus, oops, need to change back to pen. 1 minus a negative 1/3. So that means 1 over, what's that? So 3/3 plus 1/3, so 4/3. Okay, so then that's 3/4. And that is 0.75. I was thinking that it wasn't making sense before. Our r is negative 1/3 in this way because we combined the negative and the 1/3. They have the same exponent, right? So we can use that property of exponent. So r is negative 1/3. So here when I do 1 minus the ratio is 1 minus a minus 1/3. All right, so the exact sum is 0.75. This gave us 0.750800. So, but that's okay because this was just an approximation, but we can see that we are really, really close, right? If we only approximated to 2 decimal places, this will be a really great approximation. I mean, it's still a really great approximation. Okay, so that's how you do approximations of alternating series. for when it's not an alternating series, we can use the integral test. So for a series that is not alternating, we can use the integral test to still approximate the sum, right? If it converges, what's happening? Okay, sorry about that. Not sure what happened. Okay, so if it's not alternating and it converges, then if it converges, that means there is a sum. Let's call it S, just as we did before. So that means that S is equal to Sn plus Rn, same as before, right? Which means that S minus Sn is equal to Rn. So that's how we find the remainder, is the sum minus Sn, but really what we want is the sum is equal to Sn plus Rn. Now for the integral test, we can use this and say, and I can show you more in class where this comes from, but it's essentially taking an over approximation. If you remember when we did areas and we had, so if we have a decreasing series, back when we were doing integrals, right, you can do things that are an over approximation, or you can do things that are an under approximation. So your rectangles are underneath the curve or they are above the curve. And so for the integral test, what then the error becomes is we can say that the error is between the over approximation, so n to infinity of f of x dx, and above the under approximation, n plus 1 to infinity of f of x dx. So one is the under approximation and one is the over approximation, so we're in between. And so when you add Sn to both of these, then so add Sn, so you're going to have the Sn plus the under approximation is less than, right, Sn plus Rn, which is our sum that we're looking for, less than Sn plus the integral from n to infinity of f of x dx. Oftentimes it's enough to just find this part, right, because this is the upper bound, so our sum is going to be approximately this quantity. And so that's how we can approximate. So we can say our sum is approximately, or so like in the above, in this case, if it was not alternating, I could say S, right, for n equals 6, so S7. And if this wasn't alternating, I will say S7, so the sum of the first 7 terms, and then I will say plus the integral from 7 to infinity of the function. So plus the integral from n to infinity of f of x dx. And so this is a way that I can approximate the sum if is convergent but is not alternating. So it's using the integral test. And so this becomes an improper integral. So you find your Sn. So if you're using the first 4 terms, sum those up and then do the integral from 4 to infinity of f of x dx, or whatever your n is. Yeah, so that is how we can approximate. Remember, exact sums, we can only find exact sums for geometric series, because a geometric series, the exact sum is the first term over 1 minus the ratio. But if we have alternating series, now we know we can do Sn plus Rn, and for alternating series, our Rn is less than the next term. Right, Rn is less than a sub n plus 1, and for non-alternating series, our Rn is less than the integral from n to infinity of f of x dx. So we can approximate sums this way. So now we know how to approximate all kinds of sums, as long as we can find the integral. And here's just a recap of the list of tests for a series to converge or diverge. So we have just look at it, right? The test for divergence, geometric series, p-series, cookbook test, we have ratio test, root test, and those are the two that are left to cover. So I'll cover those in the next video. Alternating series test with the convergence, absolute convergence theorem, the integral test, and the Be Clever test, direct comparison test, and limit comparison test. And that rounds up all the tests. Email me if you have any questions, or I'll see you guys in class.